Alright guys, so in this video I want to show you how to draw shear force diagram and bending moment diagram for a given question. Okay, so here I am going to draw a beam, right? So let's say on a beam I have a distributed load, the uniformly distributed load of 1000 Newton per meter that distributed for 0.5 meters, right? So I have this, and then I have another distributed load, uniformly distributed load. Okay, so this line has to be horizontal, okay, of 1200 Newton meters that distributed for 1 meter. Okay, so let me draw the beam. Let's get red color for it. Okay, so the beam goes like this. Alright. Okay, and then we have another, let's say we have another point load of 200 Newton and another point load of 300 Newton, and we have another distributed load, uniformly distributed load of 500 Newton meters that distributed for 0.5 meters. Okay, so 0.3 meters, space between these two point load is 0.3 meters, and this is also 0.3. Okay, so the easiest way to draw a shear force and bending moment diagrams is by using observation and the geometry. So to do that, I'm gonna draw the outline for the graphs. So this is for the shear force and this is for the bending moment diagram. So I'm gonna say this is the x-axis, and here we have shear force, and here I'm gonna say we have moment. Okay, let me divide this too so you can get a clear idea. What it comes for different sections. Okay, so over here I'm going to do all the calculations in this side. Okay, now first thing, so because and I forgot to mention, we need supports, right? So we have one support here, we have another support here, which is called I'm gonna call this is A, and I'm gonna call this is B. Okay, so the first thing we need to find these reaction forces on the supports. So we just use the stuff that we learned during our statics class, engineering mechanics class. So I'm gonna say sum of the forces in y direction is equal to 0, right? And then I'm gonna select upward as positive. These are like general rules, like you can select downward as positive too, as long as you're consistent with that particular part of the calculation. Okay, so we have downward force from a distributed load 1000 Newton meters acts along 0.5 meters, so we have a force of 500 Newton act downwards, so it is negative. And then we have reaction force at A, which I'm going to represent as FA, which is going to go upward. I'm just going to say it is in the upward direction. Okay, and then we have another force of 1200 acts along 1 meter, so it is going to be 1200 Newton downwards. And then we have negative 200, we have negative, I can't write here because I have this guy here. I can't move that, so let me see. I'm gonna go to the next line, so it's gonna be negative 300 now, continuing from this end after the negative 200, and then I have a plus FB, and then I have another downward distributed load, so the force is going to be 500 Newton meters times 0.5, so it's 250 newtons, and everything is equal to 0, and we know the units are Newton, so I'm just going to erase this. Okay, so this is the first equation. So we have two unknowns, but we have only one equation, so we can solve this right now. So we need another equation. So we always know in statistics class we learned that we can write sum of the forces and F direction and X direction, and there is no any forces on the X direction in this bar, so there's no point of writing summation for X direction. Now we can find moments at a selected point, right? So I'm gonna say sum of moments at A is equal to 0. That way I eliminate FA. See, because FA doesn't create a moment at A because it is on that point. So by doing the sum of moments, I can find FB, right? So I'm going to say counterclockwise as positive direction. Okay, so let's see. So I'm going to put my finger here, then I'm going to analyze. So 1000 Newton meters distributed to 0.5, so we have a force of 500 Newton. And what is the distance between the force acts at the middle, so force acts over here, so the distance is 0.25. Okay, now we have to find out, is it positive or negative? So it's gonna go counterclockwise direction. So if I put my finger here, and then I'm gonna imagine if I push it downward from this side, it's gonna rotate counterclockwise direction. So it's gonna be a positive force over here. Alright. And for the second one is this one. So we have, but this one, if I push it down here, it's gonna go clockwise, so it's gonna be a negative force. So I have 1200. So the distance of the moment arm is 0.5. And then this one, 200. So let's say it's also negative, right? So 200. What's the distance? 1.3. And 300 also negative moment. The distance is 1.6. And then we have a force from FB, which is going to be, it is going to act in the counterclockwise direction, so it's going to be a positive force times 1.6. And then we have another negative force, negative moment, 250 times, so so it's act in the middle of this. So it's going to be 0.25 plus 0.3 plus 0.3 plus 0.3 plus 1. So it's going to be 2.15, all equal to 0. Alright, so by solving the second equation, so I'm going to say this is the second equation, I can find FB, the value for FB. Let me write down that number. So FB is equal to 1095.3125 Newton. Okay, so by knowing this number, I can substitute to the first equation in the place of FB, and I can find FA. By doing that, I already found the answer, so it is 1354.6875 Newton. Alright, beautiful. Now we know the reaction forces. Okay, so I can write down, so FA is 1354.68, FB is 1095.31 newtons. Alright, so what is the shear force at the end, at the left hand end over here? Okay, so there is no shear force at the end, right? So it's gonna be 0. So shear force at the end is 0. So we can see, okay, before I'm gonna explain this to you guys, I'm gonna go over some basic principles that you need to know, because I'm doing this question assuming that you forgot most of the material that you learn in your courses. If somebody know this already, you can skip this part. Okay, so I'm gonna write this equation now. So I'm gonna say change in shear force is the integration of the load, and then in the same way I can say change in moment is the integration of the shear force. Okay, this is the basic principle that we need to know in order to draw shear and bending moment diagrams. Okay, so let's see. So to find the change in shear, we need to get the integral of the load. Okay, so what happened here? So this is going to be a downward, so it's a negative distributed load, right? So it's going to be a shear force going to decrease. How is going to decrease? Linearly. Okay, so shear force is going to, I'm sorry, the shear force is not going to decrease. Shear force is going to be a negative value here. Okay, so it is going down like this in a straight line. Okay, and it is going down to, let me erase that, it went too far. Okay, hold on. Alright, so it's gonna go down to what value? So the value is gonna be the area around this this area inside the distributed load. So it's going to be 1000 times 0.5, which is going to be 500. So change from 0 to, it goes down to negative 500. So it goes down as a straight line. So it's going down to negative 500. How did I get that 500 number? that is the area under this distributed load, the first distributed load. So 1000 times 0.5. That's the force. So the shear force, so the change in shear is equal to integral of distributed load. So integral means, in other words, it's the area. Okay, so I get it. So it's going to be negative 500. Okay, so it'll be clear. So negative 500 over here now. And now we have a reaction force of 1354 acts in the positive, in upward direction. So we have a positive shear force now. So the change in shear is going to be 1354.68. So it's going to go up to, so it's going to go straight, okay? Go straight up to a value of, so this change is going to be 1354.68. So we have negative 500 here, so it comes down, negative 500 up, we have to come another 854.688 upward. Okay, and then what happened to this distribution load? Okay, so we have 1200 distributed load acts for like 1 meters long. So this is also goes down, right? Because it's a negative distributed load. So what we have in here, so the area under that distributed load is 1200. So we know this has to go down 1200. So the change in shear is 1200. So 854.688. And then we have to go down because it's negative distributed load. Okay, so it goes down to, so 854.688 minus 1200, we get negative 345.3. So now we have here, we goes down to straight like this. We go to negative 345.3. Now, in order to draw the moment diagram, we need to know at what point this crosses. It's easy. So we can, the only thing we have to do is, we know the slope of this, the shear diagram is equal to 1200, like negative 1200. So negative 1200x. So we can say in what x value this graph is equal to 854. So in other words, I'm going to write down here. So I'm going to say negative 1200x and 854.688. So x value is going to be 0.71. So this is distance between this is 0.71, and this bit is going to be 1 minus 0.71 is 0.29. That's how you fix that. Alright, now we don't have any distributed load after this one, so it's going to stay constant at negative 345.3. And here we have a negative downward force of 200, so this is going to go down again for 200, so it's going to end up becoming negative 545.3, and there's no any force here, so it's going to be constant. And now here we have upward force of 1095.31 and downward force of 300, so the net force is going to be what? So I have to say 1095.31 minus 300, so we are gonna go up 795, right? Up, so it's gonna be, so we have 545.3. Yeah, so we're gonna go up to 250 here. So we're gonna go up to 250, and then there's no any acted loads on this part. And now We have a 500 Newton meters distributed load that's distributed for 0.5 meters. So what is the change in shear? Area under the distributed load, which is 250, right? So 250 here, so it's going to go down to 0. That's how you know. If you end up becoming 0, that's when you know, if you ended up drawing it correctly. That's how you know that, okay? Because you have to end where you started. So if you started at 0, you have to end at 0. Okay, let's draw the moment diagram for this one. So the change in moment is the integral of shear force diagram. So easy. So what is the moment at the left hand end? 0. So I'll start with 0. Okay, so this is negative values increasing, right, in the first portion. So negative values, but negativity increases. So how we draw that as a slope? So I can show you here. I can erase some part here, and then I can show you. This is a little bit important. I'm gonna delete some of this stuff. Because this explanation will be very helpful for you guys. Alright, I think I'm done. Alright, so let me write down here in red pen. This is the positive slope. I'm going to write that. Positive slope increasing. How we draw that kind of a slope, positive slope increasing. It is like this. Because make an acute angle with the x direction, so that's how you know this is a positive slope. Positive slope increasing. How you draw positive slope decreasing? Like that. Alright, so negative slope increasing. We draw like this. Negative slope decreasing. We draw like this. So in the first part of this shear force diagram, we have negative values increasing. So we need to draw a negative slope increasing. Right? So we need to draw something like this. Negative slope increasing. But we don't know up to which value. We need to find which value. To find the value, we need to find the area under this triangle, which is 1/2 times 0.5 times 500. We get 125. So it goes down to negative 125. So negative values increasing. Now we have positive values up to this part. We have positive values decreasing. So positive slope decreasing. Positive slope decreasing. That's the second choice from here. So that is this guy. So it has to be positive slope decreasing up to what value? Area under this curve. So 1/2 times 0.71 times 854.688. So area under that curve will give you, let me get that number, 1/2 times 0.71 times 854.688, 303.5 414. So that's the change. So we have negative 125 now. So we have to minus that amount. So we goes up to 178.41. So we goes here is going to be 178.41. So the graph looks like, the slope of the graph look like this. Okay, this graph. And then we have again negative values increasing in this portion, negative slope increasing. We have to draw this one, negative slope increasing up to which value? So we have to find the area under that, and then that's the change. So we have to see that amount minus 178. So let me do that. 1/2 times 0.29 times 345.3. So we get 50. So 178 minus 50, we get 128. So this goes down to 128.3 something. So it goes like that. Okay, now here we have a constant value. There's no slope. Slope is 0. Okay, so we need to have constant slope, right? Constant slope. So there's no, but it's negative slope. Okay, so because negative value is constant, right? So it's gonna stay at negative 345.3 shear force. So we have a constant value, constant negative value. So we need to draw a slope of constant negative slope. So this is a negative slope. This is a positive slope because we have acute angles. This has the angles higher than 90. Okay, so negative slope, but we need to find how much it goes down. So to get that, we need to get the area under this rectangle. Okay, so it's going to be 345.3 times the distance 0.3, 103. So 128 minus 103, so we get 24.8. So it's gonna go down to 24.8. It's no curves, it's just a straight constant slope. Okay, here also constant values, negative constant values, so negative constant slope. So we have to find the area under that rectangle. So 545.3 times 0.3, so 163. So 163, we have to go change is 163, right? It's not the value, it's the change. So 24.2, it goes down to negative 138.84. So over here it's gonna go to negative, so negative 138.84. Still gonna go constant slope. This is just a one slope like this. Alright, now we have a positive numbers, positive values, constant. Now we need to draw a positive slope but constant slope, and it change in moment is going to be area under this shear force diagram. So 250 times 0.3, 75, right? So let's see, 138 minus 75, so we go to 63.8. So here we're gonna go to 63.8. So this is the change in the area under this one is the change in moment. Okay, so the change here is equal to the area under this one. So its change is equal to 75. Okay, because a lot of students make that mistake and they think this is a final value and they draw a curve up to 68. No, that's wrong. That's a change in moment. Okay, now we have to find area under this curve to find the value, which value this goes to. And then let's see, so area under this one, so this is a constant, positive values decreasing. How? The positive slope decreasing. This one, something like this. So we had to draw, okay, so to what value? Okay, so 1/2 times 0.5 times, because it's a rectangle, times 250, 62 point, yeah, so it's gonna go up to 0. So it's gonna go to 0. That's how we know that we drove this correctly. You might have like 2-3 different the difference in decimals because we round off some numbers here, but if you put exactly like all the decimal places, this is gonna come up to exactly the 0. Okay, now we are done. We draw the shear force and bending moment diagram for this problem. Yeah, so it's easy. This is a geometric method using the observation. And there is another method we can do this using deriving equations. That means we are cutting this beam at every single part. That is the original method. To do that, let me show you. I'm not gonna show you guys that method, but I'm gonna give you some. Gonna show you what does that mean. So to do that, I'm gonna cut this beam at this point, virtual cut, and then I'm going to derive all the equations. I'm going to cut it here, I'm going to cut it here, I have to cut it here, to cut it here, and I have to cut it here. So I'm going to derive equations for all of these, and then I'm going to draw this. That's a different method to draw shear force and bending moment diagrams, but this is the easiest and fastest method to do this. Alright, thank you for listening.